All right, we are going to do a brief little review of the words work and power. Work is defined as the result of a force that's applied to an object which causes the object to experience a displacement. Or more appropriately, it's a force that is applied along the same axis as the displacement of the object. So both the force and this displacement need to be vertical, or both the force and the displacement need to be horizontal. You might say that the force and the displacement need to be parallel to each other, but that's the main idea. In terms of physics, whenever we are identifying whether or not work has been done, that's what we are analyzing. Were those vectors along the same axis? So we are going to write work with a capital W is equal to force with a capital F times displacement with a lowercase d. Just to review, force is measured in newtons with a capital N. Displacement is measured in meters with a lowercase m. And so work can be described as a Newton meter, but typically what we do is we rename that Newton meter and we call it a joule. And so that's going to be measured with a capital J. We've also talked about how much work is done, which vector, which force is going to do more work when we're comparing different forces being applied to an object. So we're going to discuss that again here by looking at this image. So remember that we said that if we apply a force downward onto the box, even if that force is 100 newtons of force, if we are looking at how much work is being done by force vector C, this force times displacement is going to give me a value of 0 joules. And this is because although we have 100 newtons of force, this is not providing a vertical displacement. So vertically speaking, my force is 100 newtons, but vertically speaking, my displacement would be 0. So work done by vector C is 0 joules. If we look at the force being applied from vector A, we now have a force of 100 newtons, once again, that is being applied horizontally. So when we go to calculate how much work was accomplished by force vector A, when we say force times displacement now, we are going to have 100 newtons of force that's going to be used to create this 1 meter of displacement. So we are going to say that 100 joules of work was performed by applying the force of 100 newtons along force vector A. Now when we look at vector B, this is once again 100 newtons, but because this force is being applied along a diagonal, we need to pause and remember that all diagonals have a component that is vertical and a component that is horizontal. So if we are just focusing on this horizontal displacement of 1 meter, then we could only use the horizontal component of that 100 newtons. So when we calculate how much work is being performed by vector B, it's the force along the horizontal axis and then that displacement also on the horizontal axis. So we know that our displacement is 1 meter. Now let's just assume that we had enough information to determine that the horizontal component here is 60 newtons. So if that horizontal component is 60 newtons, then it's going to be 60 times 1. So we would have 60 joules of work performed by vector B. So C does no work, A and B both do work, but it's going to be A that does the most work because all of that force is being used to calculate the work done. So we get 100 joules versus 60 joules. Now some of the conceptual things that we need to understand are going to just focus on, is that force and displacement along the same axis? So anytime we are lifting an object, yes, work is done. The force is going to be upward to lift my object. The displacement that the object experiences would also be upward because we are lifting the object. So when we are asking you about yes or no is work done, if we are simply lifting the object, then the answer is yes, because both of those vectors are vertical. Now it says here that the force applied to lift an object at a constant speed is equal to the weight of the object. So we're going to do a brief little review of forces. This object has a force downward caused by gravity, and it has a force upward, and this would be my applied force because I'm lifting it. So we know that these two forces must be the same value in order for my object to be lifted at a constant speed. Remember, force is equal to mass times acceleration. So if the weight of this object was 5 newtons, then that means we would have a negative 5 newtons for the weight, the downward force caused by gravity. If we are saying that these are equal magnitudes, they are balanced, then that means we are applying a positive 5 newtons upward in order to lift it. So when I add these two things together, I get a net force value of 0. So remember, F equals ma. If my net force is 0, that means this object does not experience an acceleration, and that's what it means to have a constant force, okay? Now, just some additional information for questions you might see in the future. If we are calculating the work that is force times displacement, if they're asking us to calculate the work done to lift an object, then this is going to be the force to lift the object. You probably won't be given the force of the lift in the question. Maybe the question is going to tell you that it's a 5 Newton box that you are lifting. So we are then going to put in an applied force of 5 newtons times the displacement to figure out how much work was done. But what if the question doesn't tell me that it's a 5 Newton box? What if instead the question says that I have a 1.25 kilogram box? Well, if we understand that the weight of our object is calculated by saying mass times gravity, then when we get ready to calculate the work done to lift it, since the force applied and the gravitational force are equivalent, we are going to take the work and we're going to calculate it by using the 1.25 kilogram mass that they gave us. We're going to use the 9.8 meters per second squared for the acceleration rate caused by gravity, and then we would multiply that number times the displacement. So just some food for thought for future questions. All right, when we're talking about holding an object, there is no work done in order to hold an object. So when we're talking about conceptually, yes or no is work done, the answer is going to be no, because holding says that I am going to apply a force upward, but there is no displacement. There's no displacement because I'm standing here holding the box. No displacement, okay? If we are talking about carrying a box, we are also going to say that no work is done. Now, this one trips people up quite a bit, but let's think about this. If I am carrying a box, I am applying a force, and that force is upward. But if I'm, over here with my box, and then I walk over here with my box, well, the force that I'm using to hold the box in place is a vertical force. But the displacement of that object is a horizontal displacement. So the force vector is vertical, the displacement vector is horizontal. Those two are not along the same axis, so no work was done. Okay, so we have to remember when answering these questions about whether or not work was done, we need to analyze the direction of that force and displacement. All right, what happens to the work if we double the force? Work and force are directly related, so doubling the force will double the work. If we are being asked about work and distance, so I do work by pushing my object twice as far. Well, again, work and distance are directly proportional, so doubling the distance will double my work. Power is calculated by taking the amount of work that was performed and dividing it by time. So the rate at which anything is done means we divide by time. So work, once again, is going to be measured in a unit we will call joules. Time, as always, is going to be measured in seconds. So when we calculate how much power something has, we end up with a joule per second. And so just like we chose to rename our Newton meter and call it a joule, we're usually not going to call power joules per second. Instead, we're going to rename it and we're going to call it a watt. Okay, so this is the unit power. The unit for power is watts. The variable work is measured in joules. Make sure you are careful with your notations of units and variables whenever you are substituting in. Here, I just want to remind you that we need to be able to analyze the effects of both work and time to determine how powerful something is, or if we're comparing two different things. So if I have person A and they perform 100 joules of work, and then person B also performs 100 joules of work, well, in order for me to determine how powerful they are, or if I'm comparing who is more powerful, the person that does the work in less time is going to be more powerful. So if I have person A perform the work in 30 seconds, person B does the same work in 15 seconds, person B is more powerful because it was less time. Now, if we look a little bit more carefully, what we've done is we've taken the time and we've cut it in half. So time and power are inversely related. So if I'm going to take this time and I'm going to cut it in half, that means that I'm going to increase or double the power of my person. And so this is something that we've looked at quite a bit in the past. So just remember, we're still going to be asked to answer these types of questions. At the same time, if we were to say that both of my people perform the work in 30 seconds, so person A and B took 30 seconds to do their work, how are we going to say who is more powerful? Well, again, it's work divided by time, not just time. So if person A does 100 joules of work and person B does 200 joules of work, well, person B is more powerful because they did more work in the same amount of time. If we compare these two numbers, we essentially doubled the amount of work that was performed, and work and power are directly related. So doubling my work is going to double my power. Okay, so these are questions that you need to be able to answer in the future.